This is page 2 of the investigation for differentiation rules. First, we'll start with box 5 and 6, where we're going to talk about the derivative of the exponential function. So we've talked about the derivative of power functions like x cubed, where we use power rule. We've talked about the derivative of the natural log function, which happens to be 1 over x. We've talked about the derivative of the sine function, which turns out to be cosine. So now we're going to talk about the last function that you'll be responsible for knowing the derivative of, which is the exponential function. So we're going to start with one of the typical exponential functions that we've seen many times, which is 2 to the x. Okay, 2 to the x looks like this. Okay, it's an exponential function, and its value at x equals 0 is 1, like all exponential functions, right? Any base to the 0 power is 1. And then, of course, at x equals 1, the value of 2 to the x is 2, okay? And then it doubles every x value after that, right? So let's find out what the slopes are like on the 2 to the x function. You can see that the slopes down here are very small, and then quickly it gets bigger and bigger. We're going to write down the slopes here on our little table after we note them here. Okay, so we are going to check the slopes at 4 different points: x equals 0, 1, 2, and negative 1. Let's sketch the 2 to the x function. It kind of looks like that, right? And we're going to check the slope values here at 0, here at negative 1, here at 1, and here at 2. Okay, and then we're going to write those values in this table over here. Okay, so the way we're going to do that is we're going to use the manipulative that we're using before. We're just going to move the tangent line along the curve. First, we're going to move it to x equals 0, and we see that the slope at that point, we have a little slope triangle here, is 0.693. So we can write in our little table that the value is 0.693. Okay, as we expected, a small slope. And then we are going to move the tangent line up to x equals 1. And the corresponding slope is 1.39. 1.39. So we can write that in our table, 1.39. As expected, it's getting larger. Now we're going to put it at x equals 2. X equals 2, and the slope value now is 2.77. So I'll put that in our table too. Okay, and then finally we're going to move it over here at x equals negative 1. We're expecting to see a very small slope, 0.347. So here we'll put 0.347. 0.347. Okay, and then what we're going to do is we're going to see what the derivatives look like when we graph them. So I'm going to cancel out. I'm going to turn off the original function and the tangent line function, and then I'm going to turn on the slopes that we just put in our table. So we can see that the derivative values trace out something that kind of looks like the original function. Let me put the original function back. You can see that the derivative values are just slightly smaller than the original function. So wouldn't you say that the shape of the derivative values is an exponential function also? Maybe slightly smaller than the original function, right? Okay. Now to finalize our filling in box 5, I just wrote down the 4 derivative values that we took from our manipulative. So I just wrote them down here in case you want to copy those. Now let's move on to box 6. We're going to do the same thing now, except we're going to do it for the function 3 to the x. Okay, so 3 to the x looks a lot like 2 to the x, except maybe it's a little bit more steep. So here's 3 to the x. You can see it's a little bit steeper. Remember, 2 to the x this height here was 1 and this height here was 2. Now if I'm going to do 3 to the x, it's going to be height 1 here, but at x equals 1, the height is going to be 3. Okay, so it's going up steep, right? So let's collect some slope values for this function also at the values, again, 0, 1, 2, and -1. Okay, so first of all, we're going to move the tangent line to x equals 0. And the value of the slope is 1.10. 1.10. So 1.10. Okay, and then we're going to move the tangent line over to x equals 1. Okay, and the slope value is going to be 3.30. Okay, and then we're going to move it to x equals 2. Now we're getting very steep. Okay, let's type in the value. It's easier. Okay, and the slope at this value is 9.89. 9.89. And last of all, let's move our tangent line to x equals -1. And our slope value at x equals -1, let's just type it in, a little easier. The value is 0.366. 0.366. Okay, so those are the values for the derivatives for 3 to the x. I'm just going to copy them over here into this table here. Okay, so for 0, the value is 1.10. For 1, the value is 3.30. For 2, the value is 9.89. For -1, you can see the value is 0.366. And you can see if you compare between the two, you can see that the values are much higher, right? Okay, and so now let's do the same comparison we did before. Let's compare this with our original function. So let me turn off the tangent line for a second. Let's look at this. Do you see how my derivative values, which are these open circles, are slightly higher than the blue curve? Okay, slightly higher than the blue curve. So if I was to comment on the shape, I would say that the shape of the derivative curve is also exponential, slightly higher or bigger than 3 to the x. Okay, so isn't that interesting that when you take the derivative of the 2 to the x function, a base of 2, you get a slightly smaller version of itself as the derivative. When you do it with a base of 3 to the x, you get a slightly bigger version. So if you found a value between 2 and 3 that was at just the right level, can you imagine that you would get a derivative function that would be exactly the same as that base? So what's a special number that is between 2 and 3, closer to 3 than 2, right? So we basically know a couple famous numbers in high school math, right? Of course, the most famous is pi, 3.14, right? Don't we also know a special number that is between 2 and 3? Yep, it's e. Okay, so e, which is equal to 2.718, and ... If we use the e base, then if we took the derivative of the e to the x function, it would give us exactly e to the x. So that is why the e to the x exponential function is special, because it's the function where if you take the derivative of it, you're going to get the exact same function back. So that's definitely special. Okay? All right, so that is box 6, and let's move on to box 7. So box 7 is, we're going to talk about the product rule, okay? So the product rule is kind of extending all the foundational rules that we know. And we don't know that many foundational rules. We know derivative of sine. We know the derivative of a power function. We know the derivative of natural log, and we know the derivative of an exponential function. Those are the only 4 we're going to learn. But by learning structural rules that combine these 4 foundational derivatives in different ways, we can do infinite derivatives, okay? So, for example, in this particular case, what if they asked us to take the derivative of 2 things that we know how to take the derivative of multiplied together? So we know how to take the derivative of x squared, it's 2x. We know how to take the derivative of sine x, it's cosine x. But do we know how to take the derivative of the 2 multiplied together? Okay, so to explain why the product rule, which is what it's called, looks a certain way, I'm going to show you an analogy. Okay, so let's take the analogy of, let's see, we have a rectangle, and the rectangle has a certain area, and we can find this area by multiplying the length and width of this rectangle together, right? So the dimensions of the length and width, I'm going to call them u and v, okay? And do you see how this rectangle is a growing rectangle? So the original size of the rectangle is the solid line. And then when the rectangle grows, it becomes as big as this dotted line, okay? So what if we were trying to figure out the amount that the rectangle grew? The way to do that would be to define like the dimensions of how much it grew. So like the u dimension grew by delta u, and the v dimension grew by delta v, okay? And if I was to figure out the amount that it grew, what I want to do is I want to figure out the area of this border here. I'm going to break this border up into 3 pieces. First, I'm going to have a piece which is like the horizontal piece, and then I'm going to have this piece that's like the vertical piece, and then I'll have this little square in the corner, okay? So what would be the area of this horizontal piece here? It's delta u tall, right? And it's v wide. So if I was to find the area of this long thin piece, wouldn't it be delta u times v? Okay, what about this piece here? This piece is delta v wide and it's u tall. So this area would be delta v times u. And then this little square here would be delta u times delta v, right? If I was to figure out how much my rectangle grew, I would add these 3 pieces together, right? Okay, now let's fill in some of these blanks. Multiplying u and v makes an area. How much does it change when u and v grow by delta u and delta v? Okay, so in principle, it grows delta u times v plus u times delta v plus this little tiny square delta u delta v. Okay, so why am I making this analogy? Because the way the product rule looks is very similar to this. It is the derivative of u times v plus the derivative of v times u. Okay, so do you see the parallel here? Basically, instead of the deltas, I have these d's. Remember that this notation here means the derivative of v with respect to x, and it represents something very similar to the delta symbol. The delta symbol means change in u, change in v. The derivative symbol means a slope, which is a rate of change, okay? The difference between delta and the derivative is delta is usually an average change measured over a period of time. And the derivative is an instantaneous rate of change, but they're parallel, okay? So the product rule looks like this, okay? And usually when you're presented with a product on the exam, you should immediately look at the formula booklet and remember that, oh, it's a product, so I need to use product rule. It's easier said than done. Usually what happens is on an exam under stress, people tend to just take the derivative of the first element and the derivative of the second element, and they just multiply it together instead of using product rule, which you need to do this kind of cross multiplying where you multiply the original function times the derivative and the other original function times the derivative, okay? Instead of just multiplying the two derivatives together. If you notice, the tendency actually is for people to try to calculate the area of this little square instead of the long rectangles. And do you see that the little square is actually pretty insignificant to the area of the rectangles? Actually, that's the reason why this area of the little square is not found in the parallel rule of product rule, because the square is so small, it's insignificant. Okay? All right. So that was box 7. Let's go to box 8. Box 8, we're going to find the derivative of a function inside of a function. Remember composite functions, functions inside of functions? So if we know how to take the derivative of two functions separately, if one of the functions is inside the other, we can also find the derivative of that. That's pretty powerful. We can also take the derivative of many more functions if we know that we can also take the derivative of functions inside functions. Okay, so first I'm going to show you a really easy example that makes us think of maybe a possible solution, and then we're going to actually look at a more complex case. Okay, so remember, functions inside functions is when you put g inside of f, for example. In this case, I have function f, 2x, and I have function g, 3x. These are linear functions. And what I'm going to do is I'm going to put g inside f. So if I put g inside f, wouldn't that be 2 on the outside and 3x on the inside? So if I was to simplify this, it would be 6x, right? What is the derivative of 6x? Well, you might remember from power rule that the derivative is 6. You just remove the x. You might also know that the derivative is a slope. And so actually 6x is a line with slope 6. And so the slope of line with slope 6 is derivative 6, right? And remember, for 2x and 3x, similarly, the slopes are 2 and 3. So the derivatives of f and g are also 2 and 3. So you can kind of see by the relationship between 6, 2, and 3 and how we arrived at 6 here, that perhaps the way we find the derivative of a composite function is we multiply the derivatives of the two component functions. Okay, so that's our conjecture. Let's take a look at a more complicated situation and see if that works. Okay, so this time we're going to have two functions again. There's the outside function, which is x squared, and there's the inside function, which is sine of x. When we put them together, it looks kind of like this. Remember also that we could write it this way, but I wrote it like this just to avoid any confusion so that you know that the outside function is squared. Okay? How are we going to show that this follows the same logic as this simple one above? So what we're going to do is we're going to find the derivative of this function first directly by graphing it and checking out the derivative or the slope at a certain point at x equals 1. The other way we're going to do it is we're going to break sine squared up into two steps, into a squared function and into a sine x function. And then we're going to find the derivative or slope that corresponds to x equals 1 for each one. And then we're going to multiply them together to see if we get the same derivative as when we do it with the composite function. Okay, so let's do that by looking at this diagram here. Okay, you can see that I have a pretty busy diagram here. There's two things I did. One is I graphed the composite function sine of x inside squared together. okay? The other thing I did was I separated them. So I have sine of x separate from x squared, okay? Why do I have a u here? Just to review, remember the concept of function boxes? So if I have a composite function, you can think of that as, okay, I have an input called x. It goes through the function box, and out comes an output, an intermediate output, let's call it u. The intermediate output u goes into the function box f, and out comes the final output of y. Now, you might say, oh, I'm just going to ignore the fact that there is an intermediate output here. I'm just going to look at g and f together as a unit, a composite function. In goes x, out comes y. But when we work with calculus and we're looking at the slopes, we do need to pay attention to the value of this u, and we'll see why in a second. Okay? All right, first thing we're going to do is we're going to take a look at what if we just look at the composite function together. Now, we can take any function we want to and analyze it in this way because numerically, it's not difficult to find the slopes at any point in the function because all we do is draw a slope triangle and measure the two sides, right? So the thing is, to do it analytically, to do it with calculus, it is quite difficult to do sine of x inside squared rather than sine x separately from x squared. These two, we already know how to take the derivative of. This one, we don't, right? Okay, so first of all, we're going to take a little slope triangle, okay, which is this one here. We're going to draw a slope triangle, and we're going to figure out what the slope is of this composite function. So in order to do that, I arbitrarily chose a position, and I chose 1 because it's a nice number. And then I chose another position close to it, which is 1.3, in order to make my little slope triangle. All right? So the width between 1 and 1.3 is 0.3, right? That's the number here I have in parentheses, okay? And after I draw my slope triangle, I can see that the difference in the two heights I can find by plugging 1 and 1.3 into sine x squared, and then I get two values here, which are 0.71 and 0.93 y values, right? And if I find the difference between these two y values, it's 0.22. Now I can actually figure out the value of the slope because the height is 0.22 and the width is 0.3. When I divide the two, I get 0.73. So the derivative of the function is approximately 0.73 at x equals 1, right? Okay. Why is it not precisely 0.73? Well, to find it precisely, I would need to make the slope triangle really small. And if I made it really small, then it would be really hard to understand the concept of the derivative. So I made the triangle a little bit bigger. And believe it or not, even though this triangle is pretty big, 0.3 wide, I still get really close to the right value doing this demonstration. Okay, so the derivative of this function at x equals 1 is approximately 0.73. Let's verify that the rule that we use to find the derivative of a composite function, it's called chain rule, also works, okay? So what I did here is I took the two boxes and I separated them out. I have a g function and an f function. So the g function is sine of x, okay? And I took the two x values that I used above, at 1 and 1.3, and I plugged them into sine of x. And then that gives me these 2 points to make a new slope triangle, a smaller slope triangle. It looks a little lower. And the way I make the slope triangle is the same way. I put 1 into sine. I put 1.3 into sine. This time I'm putting just into sine, not into sine x quantity squared. And I get these two values here, 0.841 and 0.964. They're slightly different values than these, right? They're different because these values have only gone through the first box. In this box, don't we call this output u? So I've labeled the y-axis u instead of y, okay? Now, if I subtract these two, I can get the difference in the y-axis, and here there's different in the x-axis, and then I can find the slope by dividing them. The slope or the derivative of this first function is 0.41. Okay. Next, I'm going to look at the second function, which is quantity squared. Okay. Now, the quantity squared function, remember, is the second box here, and it's going to take as an input u instead of x. So instead of putting in 1 and 1.3, I'm going to put in these two values, 0.964 and 0.841. That's why I kind of turn this sideways. So do you see how the x-axis here, which I call u, is going to be lined up with the y-axis here because they're both u. And so now the u is going to be the input to the parabola, and then I get the output, which is going to be finally my y. Okay? And then my y corresponds to the y here. So there's a two-step process here. This is a one-step process, right? I put in x and I immediately get y out because I've combined the functions into one composite function. Down here, I've broken it up into two steps, and I can actually see my intermediate values that are between the two boxes. Okay, so I did the same thing here, and I turned it right side up here. And so you can see that when I do this process, I get two values for y, and I can subtract them to find out what goes in the top of the slope ratio, and then the 0.123 from the u-axis gets put in the bottom, and when I divide those, I get a slope of 1.79. Okay, so basically in this two-step process, my first slope is 0.41, my second slope is 1.79, and my theory is if I multiply these two together, like I did with the two linear functions, that I might get 0.73. And it turns out that I do. Okay, even though these slope triangles are not infinitesimally narrow like they should be for a derivative, they're close enough so that I actually, the math actually works out. Okay, so I'm going to write a few notes up here. So at x equals 1, the value that pops out of sine is 0.841, right? 0.841. Okay. And then when I'm sorry, I need to write that here. Okay. And then the value that comes out of the function box f, the 0.841 goes into the function box f, and then out comes 0.71. Okay. So these are just getting some values that we might need later. Okay. So this is showing you how the x values, when you plug them into the original functions, they become first u equals 0.841, and then finally y equals 0.71. Okay, I'm going to explain why we need these values in a bit. Okay, now let's test our multiplication theory here. Okay, so we already saw that if we directly do it with one step here, that the derivative of the composite function at x equals 1 is 0.73. So we can write that down here. Okay. Now, when we put 1 and we find the derivative at x equals 1 of the g function, we saw that it's 0.41. So I'm going to write that down here. And then when we do the same thing for the f function, the derivative is 1.79, right? So it turns out that if we multiply these two together, we also get 0.73. So it is a valid method of finding the composite function derivative by multiplying the two derivatives of the individual functions, okay? Now, one tricky thing here, the tendency would be, oh, let's just put a 1 here too. But remember, when you go into the f box, the input to the f box is not x anymore, it's u, okay? So here, actually, we're going to put the u value, and at the when x equals 1, the u value happens to be 0.841, right? So the value that goes here is actually 0.841. And I can fill 0.841 here too. Okay, so that's kind of tricky, and this is probably the thing that people make the mistake of most commonly when they take derivatives. They forget that the inside of the outside function needs to be the u value and not the x value, and we'll see how that actually works when we do hundreds of chain rule problems in the next month or two. Okay. By the way, this is called chain rule. And in the formula booklet, they summarize chain rule by saying dy dx is equal to the outside derivative, which is summarized with dy du, and the inside derivative, which is summarized by du dx. Why is this the inside derivative and why is this the outside derivative? Well, remember, the outside function is this second box, okay? And the second box has an input of u and an output of y. Input of u, output of y. The first box has an input of x and an output of u. Input of x, output of u. So that's why this is the inside function derivative, and this is the outside function derivative, okay? In principle, I'm just trying to convince you that we can find the derivative of a composite function by taking the derivative separately of the inside and outside function and multiplying them together. By the way, why is it called chain rule? Because when you're done, you have created a chain link, a chain, by putting these two links together. And if you have a function inside of a function inside of a function, if you have a three-layer function, the difficulty is not, that much bigger. Instead, you'll just make a three-link chain instead of a two-link chain. So when you do chain rule, you should see that you have a chain multiplication happening. And if you don't have a chain multiplication happening, then you made a mistake. Okay? All right, that's it for page 2.